The last type of problem we need to discuss in week 6 involves weak bases. Weak base calculations are going to work very similarly to weak acid calculations. The only difference with a weak base versus a weak acid is how you set up your ice table, because the reaction is going to be slightly different and you're going to have one extra step at the end. So let's look at a sample problem for a weak base. I tell you you've got a solution of hydrazine, and there's its Kb value, and it's got a concentration of 0.25 moles per liter. And I want to know the pH of this solution, and I want to know the percent dissociation. So we're going to write our dissociation reaction. Now remember, the reaction of a base with water is different than the reaction of an acid with water. In an acid, you're forming H3O+, but in a base, you're forming OH-. So make sure you look over that portion in the notes discussing the differences between a base reaction with water versus an acid's reaction with water. So we write our expression, we set up our ice table, nothing's changed, right? This is going to go up by X, this is going to go up by X. This is going to make the assumption that it's such a small quantity of change that it doesn't really affect anything in equilibrium. And now we're going to plug in our value of Kb that we already know. So x squared over 0.25. When we do our math, we come up with 4.9 times 10 to the negative fourth. Now here's how a weak base differs from a weak acid. When we did a weak acid calculation, that gave us H3O+ concentration. But there's no H3O+ in a base. We're dealing with OH-. So the OH- needs to be converted into a POH, which we then convert into a pH. So if you come up with a pH of a base of 3 or 2 or 1, you know that it's not a pH, that's a POH. The pH of a base is always going to be a number greater than 7. Right? So when you do your arithmetic, you'll come up with a POH. That'll be a low number, and then when you subtract it from 14, that'll be a number greater than 7. So the pH of a base needs to always be greater than 7. So that's one way you can check yourself. Make sure that you did it correctly, right? The pH is going to be a number greater than 7. And then now the problem asks, what's the percent dissociation? It's just the concentration at equilibrium over the initial amount. So there's my concentration of hydroxide at equilibrium. There's the initial concentration, and I multiply by 100. 0.2% is a reasonable answer, right? Because this is a weak base. So yes, you would expect these numbers to be small for percent dissociation. And there you're done.